Hey everyone, and welcome to The Explainer. Today, we're literally putting on our detective hats and stepping into the fascinating and sometimes chaotic world of modern system architecture. We're going to move entirely away from that frustrating cycle of just guessing what went wrong. Instead, we're going to build a rigorous, evidence-based framework to solve one of the most notoriously tricky issues in tech, webhook failures. If you work in technical support, you know that keeping data synchronized across platforms is absolutely crucial. And today, we're going to master exactly how to do that. Something isn't triggering. You know the feeling, right? It's a phrase that strikes fear into the heart of literally any engineer. We're dropping right into the middle of a classic tech mystery here, the silent integration failure. Two systems are supposed to be talking to each other seamlessly. An event happens on one end, but on your end, absolutely nothing. Crickets. Is your application code broken? Is the external provider failing to send the data? Or is it something as incredibly subtle as a single missing HTTP header? Okay, let's dive into this. Just imagine a super frustrated customer escalating a ticket, typing in all caps. The payment went through, but the data isn't syncing. We are breaking SLAs. This perfectly encapsulates the high-stakes reality of modern software. Customers today expect 99.9% uptime, for sure. Service-level agreements are strict. When a critical workflow, like a payment processing or a new user registration breaks, technical support engineers, or TSEs, just cannot rely on multi-day escalation cycles to the core engineering team. You are expected to diagnose and solve these integration issues in minutes, not days. So, to fix this, we first need to understand the underlying engines. Push versus pull architecture, the mechanics. Think of traditional APIs, the pull model, like constantly walking out to your mailbox to check for mail. Your system asks the server, hey, any new data? The server says, nope. 5 minutes later, you ask again, how about now? It's a traditional two-way request-response cycle. And honestly, it just eats up computational resources and bandwidth, checking for changes that haven't even happened yet. Webhooks, on the other hand, are the push model. It's exactly like having a doorbell that rings the precise instant the mail arrives. The server simply pushes an asynchronous notification directly to you the very moment the event occurs. And the efficiency gains here are absolutely massive. According to enterprise integration patterns, webhook-based push architectures actually reduce latency by up to 95% compared to constant API polling. That's a real game changer. They deliver data in near real time, often within just 1 to 2 seconds. But of course, this incredible speed and efficiency come with a trade-off. Because webhooks are asynchronous, one-way notifications, failures often happen completely silently in the background, which makes them incredibly difficult to debug without the right approach. Which brings us nicely to our next step. Deploying live payload inspection tools. Setting up an inspection tool doesn't have to be some massive engineering project. You can use a frictionless, zero-account tool like webhook.site. It's super simple. First, you just open the site to instantly generate a unique, secure public URL. Second, take that URL, plug it into your provider's dashboard, say Stripe's test node or Postman, and trigger a test event. Third, you just watch the dashboard as it catches the incoming HTTP request in real time. By doing this, you're isolating the problem. If the event actually shows up there, you know the provider is working perfectly and the bug is hiding somewhere in your own network or code. All right, so we've captured our suspect request. Now it's time to examine the evidence, the anatomy of a webhook. Let's methodically break down this payload structure because it's kind of like a giant puzzle. It consists of a few crucial pieces. First, you have the headers, which contain critical metadata and security tokens. Second, the event type. This tells your system exactly what happened, like a payment.succeeded event. Third is the body structure, which contains the nested JSON data with the actual details of the event itself. And finally, the timestamp. When you're debugging, keep in mind that bugs almost always hide within the headers or a mismatch in the expected JSON body structure. And here's the kicker. Your receiver must process this data and return a successful 200 HTTP status code incredibly fast, often within 3 to 10 seconds. Otherwise, the provider just assumes it failed and triggers a massive retry storm. Now, what's really interesting about this is security. Because your webhook endpoint has to be exposed to the public internet to receive data, literally anyone could send a fake post request to it. No way we want that. That's exactly why modern systems use HMAC, which stands for Hash-Based Message Authentication Code. It's a cryptographic mechanism that uses a shared secret key known only to the provider and your server. Basically, the sender creates a hash of the payload and sends that signature right in the HTTP header. Your system takes the incoming payload, uses the exact same secret key, and generates its own hash. If the two match perfectly, boom, you've mathematically proven the request is authentic and hasn't been tampered with. Let's put this all together now. It's time for solving a real scenario.
Let's lay out the crime scene. A payment provider, like Stripe, is sending webhook events because a customer successfully checked out. But the customer's application is failing entirely silently. No database updates are happening, nothing. The only clue the support engineer has is that the internal server logs are showing a 400 bad request error. Now, because a 400 error indicates a client-side problem, meaning the provider sent something the application didn't like, the engineer decides to route a test mode event directly to webhook.site to capture the raw, unfiltered event.
And this brilliantly illustrates what happens when we compare expectations versus reality. When we look at the clean JSON payload the application framework expects and contrast it with the raw evidence captured by our tool, we discover a glaring discrepancy. The application isn't failing because of a bad payload at all. It's rejecting the request because of an incorrect content type header. The application is strictly expecting application/JSON, but the raw webhook event reveals the provider is actually sending application/x.web-form _encoded. Hit the nail on the head. The resolution here is remarkably simple once you actually have the evidence in front of you. To fix this silent failure, you just need to adjust your server's middleware. It needs to accept the provider's actual content type header, or you need to configure a parser to handle URL-encoded data before verifying that HMAC signature. Validating the raw payload headers against what is genuinely being delivered is the absolute key to preventing these silent parsing errors. Which leads me to leave you with this final pressing question. What silent failure is hiding in your logs right now, just waiting for you to inspect it? By moving away from guesswork and applying this methodical, evidence-based debugging framework, you can take total control of your integrations. The next time a webhook fails, you know exactly what to do. Deploy an inspection tool, capture the raw evidence, verify your signatures correctly, and conquer that support ticket. Thanks so much for joining me on this explainer, and happy debugging.